Okay, thank you very much. Uh, so, my name is Ma Jian. I'm from Southwest Jiaotong University, and today I'm very glad and honored to be invited to give to share our recent research progress. Before I start, I want to express my sincere acknowledgement to the team working Australia, especially for the Professor Majid Sabi, for Milad, and for organizing the PED 2021. We were expected to gather in Australia now, but due to the coronavirus, we are now have this online conference. I think it was also because of the coronavirus. Exploring pedestrian movement becomes even more important, and it could help to prevent the pandemic spreading. Today, I'm going to talk about pedestrian descending and ascending stairs, and briefly introduce the experimental and modeling analysis in my group. Uh, Actually, I will briefly talk about in total 8 sections. Firstly, let's have a look at the research background. As we know, with the rapid urbanization process, the amount of population in Asian cities increased rapidly. To provide better commuting service, more and more modern transport facilities or infrastructures has been built, and more people are attracted to use these modern transportation systems. Early in 2030, actually, Beijing subway ridership hit 10 million, and to the year 2019, the daily ridership of Beijing, Shanghai, and some other large cities in China come across 10 million every day. Uh, so that means a large amount of passengers would use metro as their way of commuting. In metro stations and other multi-story buildings, pedestrians have to transit between different level grounds by using stairs, by using escalators, or by using the elevators. Of all these pedestrian facilities, stair is very important, and under fire scenario, it becomes the only way to escape. So, uh, to improve pedestrian traffic efficiency and evacuation efficiency in emergency situation, we need to perform a symmetric study on uh, pedestrian movement features on stairs. Actually, in different countries, they have already made their own stair design regulations or codes. For example, in China, uh, it is required that the rider head of the stair shouldn't be larger than 20 centimeter, and the tread depth of the step of a stair should be no less than 22 centimeter, and the slope of the stair shouldn't be larger than 42 degree. When we try to compare these different regulations, the different codes across different countries or across various buildings, we found that there is a large or significant difference. Therefore, The effect of a geometrical constraint of stairs on pedestrian walking speed, on pedestrian motion features, needs in-depth investigation. In the past decades, researchers from different countries has performed plenty of research on this topic. Some of them use well uh, well-designed experiments. Some of them use empirical surveys, and some of them use, for example, fire drills. Uh, these studies provided valuable and valuable data and or which could serve as a benchmark for stair design or pedestrian modeling. It can be found that the velocity, for example, uh, had uh, has a significant difference between different studies. It's not possible to compare them when the tread depth or the rider height or even the stair slope or even the pedestrian density is different. So, summarizing the current studies on this topic and considering the daily commuting experience, we believe the following factors should be considered and should be investigated. The firstly, the geometrical constraint, including tread depth, rider height, and the stair slope. And secondly, the pedestrian features. For example, do they carry luggage or carry a baggage or something else? This is very typical in our daily commuting scenarios. Let's have a look at the experiment. Uh, we, we, we want to study the stair configuration, the effect of stair configuration on pedestrian dynamics. And we know that if we put different number of pedestrians on the stair, for example, we increase the pedestrian density, the pedestrian flow will transit from free flow to stop and go waves. Uh, we want to further answer the questions such as how do people walk on stairs? How do people change their behaviors on the different stair slopes? And how does the tread depth, the rider height, affect the pedestrian locomotion features on stairs? To answer these questions, we designed and built a staircase with a top landing and a bottom landing. In between these landing areas, there are 10 steps. For each of the step, the tread depth is adjustable in the range of 20 centimeter to 40 centimeter, and with an increase of 5 centimeter. And meanwhile, the rider height is also adjustable from 15 centimeter to 35 centimeter. We also with increasement of 5 centimeter. Uh, in this way, we could control the tread depth and the rider height, and as well the stair slope. Then we put a handrail in the middle of the stair to separate the descending and the ascending pedestrians. There are two other handrails uh, on the stair to prevent the pedestrian from falling down the stair. Uh, During the experiment, we put different number of pedestrians in on the stair. We designed in total 8 different scenarios. For scenario S1, 2, 3, 4, we keep the tread depth as a constant value. We choose 0.4 meter tread depth and change the rider height from 0.15 meter to 0.3 meter. And for scenarios 5, 6, 7, and 8, we keep the right head as a constant value and decrease the trade depth from 0.4 to 0.2. And for all these scenarios, the stair slope keeps increasing. And then we performed the experiment. For the convenience of pedestrian trajectory extraction, all the participants in the experiment were asked to put on head, and the red head has a white mark on top of it. All the participants were recruited in our university, and in total about 100 participants were participated in the experiments. The experiment was recorded by a camera about 10 meter high above the staircase or the experiment platform. The video recordings was then processed by a software named PED2021 developed by Mike and Ami. And with the extracted trajectories, we can use this trajectory to calculate, for example, the velocity, the density, the velocity, by use the instantaneous measurement, or use the velocity density with the local measurements. And then let's have a look at the result. Firstly, the time-space diagram. Taken scenario 4 as an example. If when we put different number of people on the stair, when the number of people is small, which means the density is low, the pedestrians could move freely. And with the increase of the density, you can see the speed decrease gradually. When n equals 16, we can see stop and go waves emerge. And when n equals 26, we can see that pedestrian can hardly move. And to further quantify the relationship between the speed and the headway, we calculated the headway value and the speed value and show them in figure 4. It can be found from this figure. They have similar trends. They have the same variations, and as a result, we further put them into the figure, into the right figures. We further analyze the relationship between velocity and the headway. We can see that a two regime feature can be found for all the stair cases. That is to say, we have a strong constraint regime and a free movement regime. And the transition point here means the minimum walking speed or the minimum the minimum headway that is required for a pedestrian to maintain the free movement. Then we as a result, we can see, we further analyze the free movement headway features. It can be found from figure 6 in scenario S1, 2, 3, 4. Although the free moment headway decreased, but the trend, there is only a decreased trend. The number of steps occupied by the pedestrian to maintain a free movement is always 3 steps here. In contrast, from scenario in scenario S4, 5, 6, 7, and 8, the free moment headway decrease obviously, and no matter for descending or for the ascending process, we can see similar trend. Here, it should be noticed that when the tread depth is smaller than 25 centimeter, a pedestrian would like to require 4 steps instead to maintain a free moment. Here, we analyze the steps to a pedestrian required to maintain free moment. This could be used as empirical value for example, the crowd manager. They should when they should control or should manage the crowd, they can use this as a criteria to see whether the pedestrian crowd could move in the free flow state or in the congested flow state, and how it changes. And for the minimum headway, we can see similar features. For scenarios S1, 2, 3, and 4, we can see that the pedestrian can only occupy 1 step, and the minimum headway keeps almost a constant value. For small steps, which means a small tread depth value, a pedestrian would require or could occupy 2 steps instead in congested floors. This is the free movement and minimum headway features. And then let's move to the free movement speed. We know that for stair design, free movement speed is very important parameter. And in the past decades, a lot of researchers have performed empirical observations to obtain or to get the free movement speed value. Here, we calculated the free movement speed for the from the experimental video recordings for scenario S1, 2, 3, 4, 5, 6, 8, 7, 8. It can be found that with the increase of the stair slope, the mean horizontal speed of the ascending process keeps decrease. And for the descending process, we can see similar trends. For S1, the mean speed is the highest, and for S2, it is the lowest. The descending, that is to say, the descending and the ascending horizontal moment speed, free moment speed, decrease with the stair slope. And considering that on a horizontal plane, a pedestrian would like to move, for example, with a speed of about 1.1 meter per second. We then formalize, we then utilize the stair configuration of stair dimension and fit the experimental results. Here we proposed a model, a free moment prediction model by considering the stair tread depth, the rider height. We only provide the tread depth and the rider height. We can use this model to predict the free moment speed of the descending process and the ascending process. As shown in the figure 8, figure 9, and figure 10, we compare the model result and the experimental result. It can be found that the model can well capture the free moment velocity of descending and ascending process by using the equation 9 and equation 11. Finally, let's analyze the fundamental diagram. Taken scenario 3 as an example. The density and speed calculated in the former sections can be plotted in figure 11. It can be found that there's a negative relation between the velocity and the density. We can also find that there's a two regime feature. In between these two regimes, there's a transition point, or there's a critical density value. We further transform the data into the log x, and to investigate the so-called elastic effect on the density velocity relation, and then we can quantify the critical density. This two regime feature can also be found in the fundamental diagram. It can be found in the figure four, figure 40. No, sorry. This is figure. This figure. We can see there is a critical density value, and if we put all the density values, flow density values together, we can see how the stair configurations affect the pedestrian dynamics. In this figure, we can determine the maximum maximum specific flow, and when we put them in this figure, we can see with the increase of the stair slope, the maximum flow decrease, and the critical density has keeps almost a constant for the former five scenarios, and there is a slightly increase in the later three, no matter for the descending or for the ascending process. If we put all the fundamental diagram for different stairs together, we can see that for this figure, the flow rate and the density relation show a triangular feature with two distinct branches. On the left branch, we can see there is almost linear relationship between flow rate and the density. With the increase of pedestrian density, the flow rate momentarily increased. And for the right branch, we can see with the increase of pedestrian density, the flow rate decreases. However, if you remember that for scenario S1, S2, S3, and S4, we have the same trade depths. The only difference is the slope of the stair and the right head of the stair. From the fitted result, we can see that the maximum flow rate or the specific flow rate decrease with the increase of the stair slope and the riser height. And for scenario S5, S6, S7, and S8, we can see that with the increase of the with the decrease of the trade depth, the critical density increase rather than decrease. This is important, and we can see that there is a transition from free flow to congested flow, and the stair geometry, that is to say the stair trade depths, the right heads, and the slope, has an effect on the pedestrian dynamics on stairs. Okay, smart for the stair configuration. As we mentioned that in metro systems or in our daily life, we can see that pedestrians are usually taken or carrying luggage or carrying a baggage. To explore the movement of pedestrian carrying luggage on stairs in this section, we select a most common slope is a trade depth of 30 centimeter and a right height of 20 centimeter, and we further perform some experiments asking pedestrians to carrying luggage. The first question we want to answer is we want to know is the influence of weight, baggage weight on pedestrian movement features on stairs. Uh, we thus selected or set four different scenarios. Uh, uh, we asked the pedestrian to carry 3 kilogram luggage, 4.5 kilogram baggage, 6 kilogram or 7.5 kilogram baggage with them when descending and ascending the stairs. In total, 20 different pedestrians were recruited, and the ratio of female and male is 1 to 1. So after the experiment, we can extract the pedestrian trajectories and plot the time-space diagram as what we found before. Here, for uh, the four pedestrian ascending process, this figure shows four pedestrians carrying 3 kilogram 3 kilogram baggage, and for this one we can see that it represents the 20 pedestrian scenario, and for each of the pedestrian, the pedestrian carries 7.4 kilogram baggage, and similar to the findings in the experiment where pedestrian carry no luggage, we can see firstly, when the number of pedestrians is small, the pedestrian can move freely, and with the increase of the pedestrian number, the speed decrease. And when, for example, here we can see when the number of pedestrians in the experimental run is 16, sub and go waves emerge, and when n equals 20, pedestrians can hardly move, and the stop and go waves becomes more obvious. This is for the ascending process. For the descending process, we can see similar trends, and there's no obvious difference of pedestrian spatial distribution for different baggage weights under the same global density, whether it's ascending uh, or, or descending. We further plot the density, velocity relation, density and flow relation here in these figures. It can be found that there's no significant difference in the fundamental diagram when the baggage barely influence on the pedestrian moment. So that we choose 3 kilogram as the baggage weight and perform further experimental study to check the baggage laden ratio on pedestrian movement feature. Here, we use 50 male, and we divide the luggage laden ratio into 5 categories. The for example, here for the first category, none, no pedestrian were asked to carry luggage carry a baggage with him. For the low ratio category, we ask about 20% of the pedestrian to take baggage with him, and for the medium, high, and full categories, we asked some of the pedestrians to carry the baggage with them during the single file moment. Um, okay. Firstly, we let's have a look at the individual velocity feature. The mean and the standard deviation of the individual velocity has been shown in this figure. As can be found, the descending process, the mean velocity for the descending process is larger than the ascending process. Uh, for male, this is true, and for female, we can also find the descending velocity is larger than ascending velocity. But when we compare the cases with baggage and without the baggage, we can see that baggage laden would reduce male's speed, while this behavior has no significant effect on female's speed. This is quite interesting, but we still don't know why, but we have found this phenomenon. And for the relationship between speed and density, we can see that the baggage-laden ratio has barely effect on pedestrian movement feature. We further transit the speed density relationship into the log x and fitted the resulted line. We can see that we can also see a two regime feature for the um, for the free flow regime. We can see there's no significant effect of bucket latent ratio, and for the congested regime, we can see that the pedestrian velocity becomes more sensitive to the density change. Uh, that is to say, as the ratios of backlighting increase, the velocity of pedestrian becomes more sensitive to changes in density, and the velocity of this ascending process is more sensitive to the change of the than the descending process. This is for the speed and the density relationship. For the uh, flow rate and the density relationship, we can also find that at low densities, there's no significant difference in the relationship between density and the flow. But for the high density regime, we can see the flow rate gradually decrease if we increase the ratio of luggage laden pedestrians in the descending and in the ascending process. But the discrepancy is more obvious for the ascending process uh, rather than in the ascending process. The velocity drop rate in the ascending process is more sensitive to the change in density, uh, which further resulted in the rapid decrease of the flow rate. At last, we analyze the headway speed relationship. Uh, from the fitted line of headway speed relationship, we can see two uh, two regimes. The first one is the strong here of the strong constant regime slope of the ascending process, we can see that the adaptation time gradually increases the increase of pedestrian luggage laden ratio. This regularity doesn't hold for the descending process. We found no clear trend of the adaptation time in the descending process. As the increase of the pedestrian luggage laden ratio, the minimum headway here we can see for the low, the red one for the low, and this one for the medium, and this one for the high, and this one for the full. The minimum headway gradually increases. And for the second regime, we can see uh, the free speed and the minimum free walking distance. Clearly, for the descending process, we can see the descending speed. Uh, the descending speed is higher than the ascending speed. Uh, the minimum free walking distance increase with the pedestrian luggage ratio, no matter for the descending process or the ascending process. This is the baggage laden ratio on pedestrian movement feature. As we mentioned, when we can carry luggage or we can carry baggage, we can see some pedestrians carry luggage, some pedestrians carry baggage. Here, we further replace the baggage with large suitcase and recruited some other participants here in here in this experiment. We have 16% female participants and 40% male participants. And we also divided the luggage into five categories, the luggage laden ratio into five categories. That is the non case, the low ratio case, the medium ratio case, the high ratio case, and the full case. And we can also analyze the individual velocity from the result showing this table. We can see that the descending process, the descending velocity is larger than its ascending velocity for the males, and for the females, the descending velocity is also larger than the ascending velocity. This is uh, this is similar with the former one when we ask the pedestrian to carry baggage with them. However, if we compare the ones with luggage and without luggage, we can see that there's no significant difference between the ones uh, with or without the luggage, no matter for the males or for the females. For the fundamental diagram, we can see that the luggage laden pedestrian is affected in the descending is affected in the descending process much obvious than the ascending process. And for the as the ratio of luggage laden pedestrian increase, velocity of pedestrian is more sensitive to the change of uh, the density, and the velocity of the descending process is more sensitive to the change in density than that of the ascending process. This can be found when we compare the slope of the fitted curve in this figure. And when we compare the fundamental diagram, we can see that at low densities, there's no significant difference. And except for this one, for the high ratio descending process. And at high densities, flow rate gradually decrease as the increase of the pedestrian luggage laden ratio. This is similar with the one in the baggage laden cases. And uh, we further analyze the headway speed relation. As can be found in this figure, we can see uh, there is also a two regime feature or two regime pattern. For the ascending process, and the descending process, we can see the strong constraint regime. Uh, uh, the fitted line of the strong constraint regime reflects the adaptation time. During the ascending process, the adaptation time, which means the slope of the fitted curve, increase as the ratio of the luggage laden pedestrian increase, while it firstly decrease and then increase for the descending process. As the ratio of the luggage laden pedestrian increase, the minimum headway tends to increase, but some of the cases doesn't fit into this pattern. And secondly, we can see from this figure, the free movement speed of the descending process is larger than the ascending process. Uh, when we compare the minimum free walking distance, we can see that it almost increase with the increase of the luggage laden ratio. Here for the ascending, it also we can find the it, the, the similar trend. Okay, this is for the effect of the luggage laden ratio. If we compare these two different experimental settings, the only difference is that we in the former one we use baggage, and in the later one we use luggage. Uh, when we put the results together, we can see that the average velocity of a luggage laden pedestrian is greater than that of the baggage laden pedestrian, both in the ascending and the descending process. Uh, as we can see here, the green curve represents the speed of the descending pedestrian who is carrying a luggage with him. This the value of this the value of the speed is almost the topest because it's the largest one. Uh, this is in contradiction with our feelings because when we carry baggage and we believe it's convenient, but when we carry luggage, it seems heavy, and the speed should be slow, but in the experiment we can see the speed becomes higher. And the reason for this difference is that holding a large suitcase is not comfortable for the pedestrian. Thus, a pedestrian want to speed up so that he can have a stop at the landing area during the descending process. For the ascending process, we think holding a large suitcase is also notable. The pedestrian may want to speed up, but due to the extra weight of the luggage, he cannot speed up as he can do in the descending process. The difference of average velocity between the carrying luggage or carrying baggage decrease with the increase of the pedestrian density and with the increase of the increase of the luggage laden ratio, as shown in the figure. And from the flow rate density diagram, we can see similar trends. At low densities, the flow rate of luggage laden pedestrians in the descending process is significantly higher than other cases, while the maximum flow values, for example and here, are higher than the ones of the descending processes are higher than the ones of the ascending process. This is the experimental results. And at last, we want to have a look at the minimum headway of pedestrian carrying different luggage. It can be found from this figure. The minimum headway of carrying luggage is larger than the one of the carrying baggage case. Carrying a large suitcase here uh, it means that the minimum headway is a little bit larger than when carrying a baggage. When we check the minimum free walking distance, we can see that the minimum free walking distance for luggage laden cases are greater than the baggage laden cases. This is due to the reason that the large luggage occupies some space, and pedestrians, as a consequence, cannot get too close to each other. So the minimum headway and the minimum free walking distance becomes a little bit larger. This is all the results for the experiments. From the experiments, we can see that stair tree depths and rudder height and the stair slope are uh, uh, these factors play important role in determining the pedestrian moment on stairs. Uh, when we look at the descending and the ascending process, we can see different features. And as a consequence, when model the pedestrian movement on stairs, we should consider the gent features of level ambulation, stair ascent, and stair descent. For example, here, when ascending, a pedestrian should first lift the lower foot to the level of the target head, and then put the head a little bit further to the target step. Uh, and when descending, the pedestrian would move his upper foot a little bit forward and then move move the foot along the incline of the stair to the target step. So comparing the ascending and the descending process, the footstep lengths are not equal to each other when descending and ascending. So we, as a result, proposed a footstep equivalent footstep line concept in to describe the moment, the difference between ascending and descending. We calculate the footstep length according to the following rule. For example, for the ascending process, a pedestrian want to move from point A to point B. The footstep length is the footstep line is ACEB. It's assumed to be ACEB. But for the descending process, as we explained, For example, a pedestrian wants to move from point B to point A. The footstep line is the BEDA. And clearly, line ACEB is longer than BEDA. From the right figure, we can see the equivalent footstep line shows discontinuity. That means when ascending, when ascending, a pedestrian can move only a small step, but when descending, the pedestrian could go a little bit further. This is the difference between ascending and descending. Based on the experimental findings and our analysis to the footstep trajectory features, we follow the cognitive model and the social force model and propose here a footstep model to quantify the pedestrian movement on stairs. Our contributions lies in three aspects. Firstly, we introduce the gen features into the desired speed calculation. And secondly, the pedestrian agents in the model occupy space of a wiring area, which means the size of the pedestrian could vary. In this way, the densely packed situation could be simulated. And thirdly, we introduce a geometric constraint of the trade depth into the model. And here, we use a stop probability to reflect that a pedestrian has a delayed reaction, which is called adaptation time in the form analysis to the movement of the pedestrian in front of him. So in this way, we can we built a model and we can simulate the pedestrian movement on stairs. Before we perform further analysis, we should further validate and calibrate the model. The single file pedestrian movement experiment was used to calibrate the model, and therefore, in the simulations, we use periodical boundary condition to simulate the experiment. Periodical boundary condition here means when a pedestrian moves out of the system, he will go back to the start point and enter into the system to keep going forward. And we put different number of pedestrians on the stairs. When the total number of pedestrians is small, we can see they can move freely. With the increase of the total number of pedestrians, we can see that the stop and go waves emerge. And after calibration, we calculate the speed density relationship for the descending and for the ascending process. We can see that the speed density relationship of the simulation results go well with the experimental results. And the stop and go waves has also been formed in the simulations. After calibration, we want to validate the model before we perform a further analysis. To validate the speed density relationship, we use another stair geometry. Here, we performed a field survey and collected the data for pedestrian descending and ascending on a stopped escalator in University of Hong Kong. And then we performed simulations by using the stair geometrical features, and we compare the survey and the simulation result. We can see the simulation results go well with the field survey results. Uh, that means the model has a good generalization ability. Then uh, we can perform further analysis. We set up a high level ground and a lower level ground and put a different number of pedestrians descending and ascending the stair. And uh, during and we change the width of the stair from 1.2 to 2.8. With the increase of the stair width, we can see for the ascending process, initially there are two lanes, and here there are three different layers, four, and here it's the when the width of the stair uh, becomes larger, the layer formation phenomenon is not obvious for the ascending process, but for the descending process here, we can see clearly there are five different lanes. The result of the stepwise growth of number of lanes fits well with the empirical study in Ogando and Damon's research. This is the self-organized layer formation. And when we check the effect of rider height and tread depth, let's take the ascending process an example. For example, for a given rider height, we can see the speed increase from a lower one to a higher speed value. That means when the rider height is constant, it's a constant value. We increase the tread depth, pedestrians on the stairs can move faster. This is quite interesting, considering that the different combination of the rider height and the tread depth would result in uh, a similar or a same stair further fix the rider height and plot the speed of the pedestrian uh, in the speed stair gradient diagram. And we can see that with the decrease of the stair gradient, the speed increase. This is in good agreement with the experimental findings, and we can also find that there is a transition point from the increase of the gradient. The transition point here, for example, when the rider height is about 22.8 centimeter, when the firstly the pedestrian speed decrease with the stair decrease, and after about 27 degree, the speed doesn't change. This uh, critical gradient increase with the increase of the rider height. And for the descending process, we can have a similar pattern of the speed profile. And here, the descending pedestrian usually moves faster than the ascending process. As a result, we can see the red color occupies a large part of the different rider height and the tread depth combination. We then simulate the pedestrian movement with different number of pedestrians. We increase the number of pedestrians to be evacuated uh, from from the building. We can see that with the increase of pedestrian number, the evacuation time increased. And for the descending process, we can see it's always faster than the ascending process. Um, with the increase of pedestrian number, the evacuation time difference, firstly, is very small, and with the increase of the the pedestrian number, it becomes larger and larger. And then uh, the timing is up. Okay. I have only got 3 slides more. I will finish as soon as possible. Okay. With the we then simulate the effect of a step width, and we can see with the increase of step width, the flow rate, uh, uh, the flow rate increase linearly with the increase of step width, and the difference between flow rate of the ascending and the descending processes is small for narrow stairs, but for larger stairs, we can see the difference become larger. So that means when design a stair, not only the stair width, but also the flow direction matters. And to conclude our research, we can see that we have built a staircase to perform a symmetric analysis of pedestrian movement on stairs, considering the pedestrian is carrying a luggage or baggage, or with no baggage. With this insight into the pedestrian movement on stairs, we formalized a footstep model, and this model is capable not only simulate the pedestrian movement on stairs, that means the descending and ascending process, but also on level ground. So we applied the model into the pedestrian flow analysis in metro stations and in, for example, high-rise buildings. We are now validating the model by comparing the modeling the modeling result with a real evacuation performed in a 77 floors building evacuation scenario. The evacuation took about 1 hour, and our initial results indicate that the simulation fits well with the fire drill. Maybe in the future, I can report the results on that. At last, I want to acknowledge my all of my co-authors and the research fund, and that's all of my talk. Thank you. Yes.